Now that we've gone over Newton's three laws, now we're ready to see how they fit together in the broader context of the world of physics. And each of Newton's laws was really revolutionary in its own right, and combined they create a really new and interesting way of thinking about physics. And the first big breakthrough Newton had is instead of thinking about physics in terms of things like mass and velocity and acceleration, he thought about it in terms of forces. And this is really important because if you think too much in terms of mass, velocity, and acceleration, it can be really confusing. Why does a thrown ball fly in a parabola? Why does the Earth go around the sun in a circle? Is there something special about these shapes? Like, what causes these specific geometries? And no matter how hard you think about it, these can still be very confusing. A lot of very smart people tried with very little luck to figure out what was going on. And Newton thought of it in a much simpler context. He instead thought about it in terms of forces. He said a ball that's being thrown is under the influence of gravity. He said that the Earth going around the sun has gravity and velocity, and that's what causes its motion. And as a result, he discovered that even though forces are invisible a lot of times, you can't see them, and thus it's harder to imagine what's going on. If you make the jump, if you make the effort to think about it in terms of forces, everything gets a lot easier. And as I'm sure you've noticed, every one of his laws talks about forces. The first two go together very strongly. They say that when force equals zero, acceleration equals zero. And then the second law says force equals mass times acceleration. And when we plug in zero for force, we find out that zero equals mass times acceleration, or zero over mass equals acceleration. And zero divided by anything is always zero. So we just say that acceleration equals zero. So what we discover is the second law is actually a more general version of the first law. Now the third law is a little different. It also talks about forces, but it's looking at forces as split between objects. And this becomes very important for later lectures. Whenever we talk about momentum or moment of inertia in rotating objects, all of these concepts can actually be traced all the way back to the second law. And this law, that the equal reaction leads to the opposite reaction, is very, very important. And by combining these laws, we can actually do some thinking about objects in general. For instance, what would happen if I have a marble sitting on the ground and another marble rolls into it? Well, we can think about it in terms of forces. As long as the marble's just rolling, there's no forces being acted upon it. Or more specifically, there's no net forces. The sum of forces equals zero. So as long as the sum of forces equals zero, it shouldn't accelerate. But once it hits the other marble, then we have an action. And the first marble is being pushed backwards, and the second marble is being pushed forwards. So now there should be acceleration, the velocities should change. And the first one's actually going to come to a halt. It's going to stop going. But now because it stopped going, that means it exerted a force on the other one. So now the other one accelerated in the forward direction, and since it had the same mass, it accelerated forward the same amount the other one accelerated backwards. And what this means is now the second marble is rolling along, and pretty soon we're going to see that it's rolling on its own. So we were able to combine all three of Newton's laws. We first of all said the first law up here, that since there's no force, there must also be no acceleration. Then when they hit, we looked at which direction the forces are being applied, and applied the second law. And we said this one has a force in the backwards direction, so it's accelerating backwards. And this one has a force in the forward direction, so it's accelerating forward. And then we applied the third law. We said that these forces must be equal and opposite, so if this one comes to a halt, the other one must then continue moving. So while these three laws of physics are very powerful on their own, combined, you can use them to solve almost every common physics problem. Now this won't be true as you get to things like magnetism and electricity, but for the physics of mechanics, where things are flying around and hitting each other, almost all of physics is understandable through these three simple laws. And now that we understand these three simple laws, we're ready to go on to the final step in free body diagrams, which is, as we've mentioned before, you draw your object, you draw all the forces that are acting upon it, whatever those may be, and then we have to talk about acceleration. And now that we understand Newton's three laws, we can look at his first two laws, and we either need to write that the sum of forces equals zero, and thus acceleration equals zero, or we need to write that the sum of forces equals mass times acceleration. And by doing this, we finally have enough variables to solve problems like this. And in later lectures, we'll go through and see exactly how we can solve problems like this. And different problems require different techniques, But it's very important that by setting up the free body diagram exactly like this, by using the equation either F equals ma, or that net force is 0, so acceleration is 0, and by drawing all the forces on the object, we then are able to write equations and solve them, and find whichever variable we happen to be looking for. So I hope you understood that. If not, go back, maybe rewatch some of the lectures in this unit, and then you're ready to move on to the problems.